All right, so I'm gonna take you through, and this is just incredibly mad, but let's sort of talk through a very simple thing, which is derived from all of this, and actually comes out of teaching this course, and like going back to these things and thinking about something, some simple ideas. So I think the key thing is we're going to have d-dimensional, a d-dimensional ambient space. We live in 3 dimensions, and our sinks, our capillaries are in filling a 3-dimensional volume as well, right? And that's true as we go across organisms. But if we think of something like a network that's actually in a 3-dimensional space, right? There's height, right? So they can get deeper and so on. And when we look from the above, we're not really worried about it too much, but that's true. But it's really a 2-dimensional, it's a little rough and so on, but it's really a 2-dimensional thing inside 3 dimensions. So that's a key piece. That will mean a lot later on. So we're going to assume sinks are invariant. So we're going to use a lot of the things they've done in these other 2 papers, or these other 2 lines of work, I should say. There's some sink density. So this captures the idea that maybe for elephants, the capillary is servicing a bigger volume than it is for a mouse, and the whole thing runs at a bit of a slower rate. Ben, who was in POX last semester, gave his students in calculus a question, and it was about the fastest speed, right, that I showed you again for the scaling of organisms as a function of mass. And the students were able to figure out that a 0 mass animal maximum speed is 0, because it doesn't exist. And then in the limiting case, and the infinite mass one just never starts. So, yeah. So it's good. Math. Right, but this is, that sort of fits in, this idea that the bigger ones, it's like harder for them to get everything running. Okay. There's going to be some cap, the flow of speed of material, right? That's not going to, you can't have that scaling in some way that'll go through the roof. It could increase, but not scaling, right? And we'll try to take this network as a bundle of virtual vessels, which we know is not really true, but this is just going to be an abstraction. So here's a heart supplying these 3 pieces, or whatever we think is our source, applying to 3 sinks. And so this tube, or the amount that's being delivered here, equal amounts being taken being siphoned off here and here and here. So you need, whatever it is, 3 units per time coming down to this first one. They split off, so 1 gets taken in, 1 gets taken in, 1 gets taken in. Fair enough? So we'll just say this is actually a network that's structured like this, that it really is these 3 little pieces, and they're just packaged together. And we're not going to worry too much about the fact that we're away from a braided structure. We know that actually there's goodness that comes from the material being combined together, right? Less impedance and so on. I mean, it's sort of funny, right? There's the less impedance, so networks make sense from that point of view, but also just like you would never be able to get, you have to have some pretty, okay, so what you could have is like a little tube from the heart to every capillary, a separate one, right? Just be like this whole bunch of tendril, it's pretty yucky, but this whole tendril-y thing, and each one has its own little tube, which an engineer might make or something, right? I mean, you sort of could do it. And so you'd be delivering all these little blood cells, and it would be just a disaster. So, all right. Evolution's not going to produce that because, So, number of sustainable sinks, how does that scale with volume V? So you're increasing this thing. There's just a single central source, so that's an issue, right? And as you get to higher and higher dimensions, you're going from a 0-dimensional source to 1, 2, 3, 4. That's a harder thing to work with. And what's the highest scaling we can get for this? The number of sinks is a function of volume. That's what we want. Right. So there's a really beautiful thing I think that's going to come out with surface area and network structure. They're going to match, only in one special way. That's going to be 2/3. But, For some reason, a lot of those papers I just showed you, they don't talk about the bird stuff, right? The bird scaling is super duper 2/3. So, you know, like what's going on? I guess someone's trying to invent a 1,000 kilogram bird so they can show that it deviates in scaling. All right, so let's imagine we got a family of shapes, and they could be all sorts of shapes. We're just going to do it pretty generally. And here's our splattered eggy thing. So it's going to scale allometrically. So we're going to have 2 length scales for this one. And this omega is going to represent this shape, and this V is a parameterization, which is, so it's in general, right, it's volume, but this is area, of course, for 2 dimensions. And then we're going to have these length scales. They're going to scale the overall volume to some power. And because, right, as we multiply length 1, in this case length 1 times length 2, we need that to be proportional to volume, as with scaling. So these exponents have to add up to 1. Right? So if it's isometric, the exponents will be this length scales as area to 1/2, and this length scales as area to 1/2. For 3 dimensions, the lengths would scale as volume to the third, volume to the third, and volume to the third. And that's what this is. So for isometric growth, we'll have 1/3 for 3 dimensions and 1/2 for 2 dimensions. They're the ones we're mostly going to think about, but in general, it's 1/d. And for allometric growth, you just have to have 2 of them different, right? Some separation away from 1/d. So there are some interesting extremes. Here are the extremes, right? Yes, I have to do that. The spherical. That's a hilarious joke. Assume spherical cow. Yeah. All right. So here's our scaling. So in this case, we have the 3 length scales, right? We orient some lengths, like an axis around it here. The 3 length scales are going to be scaling as volume to 1/3. And in this case, there's going to be, let's just make it like this. We're making a pancake cow, so it's just instantly delicious, right? I mean, yeah. So the burger cow. Yeah, that would be better. Or it could be a tofu burger, that's fine. So this is, it's got some thickness, but it's just, and that doesn't grow. Or you can imagine it just grows very slowly. It doesn't scale, you know, logarithmically or something like that. But these are, this is an important scientific piece, right? Okay, so these lengths are going to scale. So in this case, they'll scale as volume to 1/2, right? This is going to scale as volume to the 1/2, volume to the 1/2, volume to the 0. So this one times this one times this one gives you volume to the 1/2 plus 1/2 plus 0. So volume to the 1. Coolness? So it's cool. Yeah. And then you want to think about surface area for these things. So surface area, in this case, is going to scale as volume to the 2/3. But this one, the surface area, is going to scale in a different way, and it's going to be, and this is actually a problem that was in Parkes, but it's volume to the power of 1 minus the minimum scaling exponent. It's a nice thing to figure out. Right, so the surface area around here doesn't really matter. It's dominated by the fact, that this is the slowest scaling, and in this case, sort of a non-existent scaling. The surface area, because these 2 length scales are scaling like volume to 1/2 times volume to 1/2, and that's length 1 times length 2, that's the surface area, right, for this thing, yeah? Plus, you know, length 3 times length, you don't have to worry about that one, right? That's not it's going to be insignificant. But that's, so in this case, surface area is actually scaling like volume as well. So this is a really, and then you're going to have some network in here, right? And it's just like increasingly disturbing internal aspects of this cow, right? So there's going to be some heart in here and some udders. The whole thing's a mess. Anyway, but it's going to have to spread out like that, which you can imagine, you know, so for a river network, that's kind of what's sort of, right? We're going to have that sort of thing. Or a city, you know, you can imagine there's a city here and we've got to get everyone inside. Not a cow. But you have your city and you've got people trying to get in. That's a kind of a common kind of thing. And your city is growing, or you have a collection of cities. Yeah. So that's a pancake cow. All right. I made the important tarot cards. Okay. So I just kind of told you, but it's a nice little thing to think about. You can actually just, you can do it abstractly, or you could think of parallelepipeds, right? You can make yourself little rectangular blocks. Okay. A tofu loop, right? Okay. And then, so this is general families of regions. How does this work, right? Okay, this is good. Okay, good. So it's going to matter. So this is consistent with what Bannevar and so on. I mean, it's just an observation, really. Like, if you want to make the best and worst kind of networks, and I sort of alluded to this before, if you had your own little, private tube that took you from downtown Manhattan to your house, and right, and you don't have to be with everyone else in the subway. Or, you can be in your little special car and so on. We sort of do it with cars, right? We sort of do it. But the traffic will actually affect you, and you will be rude and sad. But imagine you have your own tiny little tube, and you get in and you go, whoop. Okay. So we could have that. That would be sort of our best configuration, right? This will be a disaster, and it's kind of like the same thing where you travel, you basically fill space. You travel everywhere before you get there. This is your random walk sort of thing. And this could be constructed if you say, I'm actually just going to have one person deliver everything and they have to walk to every place, right? That would be a terrible idea. Which happens with school buses, though, a little bit, right? So, you have your school and you have to get dropped off. So the bus has to go to all these places. Okay. Which is really tough. So, when I was a kid, actually, it's like 15-kid elementary school that I went to. In the morning, really early, it would take us 3 minutes to get there because we were the last ones picked up. But after school, we drove around like 20 miles or something, and then we were the last ones to get off. Never really thought about it too much. Okay. So, there's this very clear statement. The minimum network volume you could have is one that's proportional to all the distances from the source of the sink, right? We have all these little tubes that they're delivering. They're all the same size. They're not really, growing or changing with overall volume. The elephants, you're trying to get the same amount of stuff to a capillary. Capillaries are capillaries. Humans in their little cars are humans. So this statement is clear. That's the best thing you can do. And in fact, this is Gassner and Newman, which we talked about in POX, but it's just quickly again. This is taking a real network. It's the T is kind of in here, and then this is the commuter rail network for Bostonian peoples that's out here. So, if you want to get from one place to the other, that's a bit tricky if you want to stay within the commuter thing, but of course, if you're trying to get to the central part of Boston, then it functions quite well. And this is where everyone has their own special little, thing. Boston is a bit funny too with the T because there's the red line and the blue and so on, and the green line has the little splintering ones, right? It has the little smaller ones that do actually kind of break off. So they have sort of a mixture of solutions. They've done a couple of different things. This is a minimum spanning tree, which is just a bit of a funny thing to do perhaps for this, but like this one got broken off. Right, no loops in that one. And then this one is the work that they do in this model to sort of construct in this paper to construct a minimum one. And it's quite good. It fits this pretty well, right? I mean, there are wiggles because of the way things got built and there's geography and so on. And these are just going to be straight lines. But the point is the one that Boston actually produces is pretty efficient. So equations can do it. Slime mold can also do it. This is a science paper, just great achievement by humanity here. This is a Japanese group. They put down all the stations. They made a little a plate that has locations of cities or major stations around Tokyo, and then put a slime mold in it, and then put the food there, right? And then let the slime mold grow. So they put food at the stations, let it grow, and then it thins out, and it's like it's a blob to start with. Slime mold, which I guess is super interesting, but it's not a, just doesn't, I mean, it's super interesting in its, it needs a better name. And then it thins out, right? Yeah. And it actually fits, it conforms pretty well to rules for biologically inspired adaptive network design. Excellent. It's pretty interesting, right? So it's trying to feed itself and do it in an optimal way. And it works out. Okay, so there's a video you can watch there too. Yeah, fun. Okay, so here's a simple, look, so let's try this. We're going to imagine a little bit more. We're going to say, here's our source, and here's our sink, and we can imagine that maybe the tube changes in size, right? So, and the reason for doing this is it's going to come fast out of here, kind of shooting out of the origin, and if this was a fluid, then it slows down because this widens up. And this is very exaggerated. This is true, actually, basically what does happen in the blood network, because it's slower at the outer branches. And so that's one way to just build it in a geometric way, where there's no physics in this, but we could just say, so that might work. But this can't really scale with size in a way that matters, right? If you can play around with this and figure out what the volume of these odd shapes are, and it's not going to be something that contributes, right? We could try to put in a scaling so the radius is tapering from the sink, where we know what the sink is. We can imagine the tapering, like we specify what the outer part is. We want it to be going at a certain speed here. And the volume was going to scale as length to 1 minus 2 epsilon, or 1, depending on how epsilon is. So there's some nice little results in that. It's really detailed silliness, I suppose, but it's there. Yeah. Right, so for large enough length, it doesn't matter in this case, but there is a minor scaling if epsilon is less than a half. Fine. So then we set this up. The minimum volume, we're going to have a density of sinks across our shape. So this is a function of x. And then for every one of these sinks, just like that slime mold or whatever, every one of these little places that we're going to, or the commuter stations, we say, okay, this is the volume of the special tube that goes to that sink. Right, it's a sort of funny fluted thing, or you can imagine just a straight straw, but we're kind of imagining a more general thing. That's the volume we can put in there, right? And this is for epsilon less than a half. If you do this calculation, and you can do this for arbitrary shapes. It's a nice little it's a nice thing. Then you end up with this result. So this is going to be the minimum of the volume is going to scale as density, and then the overall volume of the shape, right, as 1 plus, and so gamma max is going to appear in here. The maximum scale is going to appear in there. So that's a cool thing. And if epsilon is a bit higher and we don't have this, then we end up with this network volume of scaling as rho to the v, right? So it's density times the volume. Good. That's good. Now, that scaling is not really going to be an issue too much. So if epsilon is 0, then the really big result is here, I think. So it's going to be density, volume to the 1 plus gamma max. So this is where the allometry of the shape comes in. The network is trying to supply this thing. We're thinking about this shape over many scales. The network required to, so what this is saying is the network, so gamma max is here. This is going to increase, right, as gamma max gets bigger, which means it becomes more of an, further away from being isometric, more allometric, right? So the pancake cow thing will have a half here, and the spherical cows will have a third here. So the pancake requires a bigger network. The scaling of the network has a higher exponent with respect to the volume of the thing it's trying to feed. Right, so it's less, it's more costly in terms of infrastructure. Right, so a ball is easier to build networks into, and you have to be careful about thinking that, because you think, okay, it's a ball, but you have to think about how it scales, right? So as we move up through bigger and bigger spheres, the way the network scales, the minimum, this sort of optimal network's volume, the way that scales is as low as possible. If it's a pancake series of pancake shapes, then the network, the minimum network that you need to supply everything, it scales in a way that's a higher power of the volume, right? You need to make more network. Eventually, you'll have more network, right? Okay. Yes. Oh, okay. Okay. So these are these pieces. So scaling is isometric. Then we have this. We put 1 over d in there. If scaling is allometric, we're just going to say gamma max is this gamma allo, just like whatever it is. It's greater than 1 over d. It's larger. And this is this point I just said, right? So that the minimum network's volume for the isometric one versus the allometric one, that ratio goes to 0, right? So this is as we go up through volumes. So you need less network to supply a isometrically growing series of volumes. Okay, good. We're gonna make it. Caffeine is not wearing off. Okay. We can worry about this one. So the network volume it's not even dependent on the overall shape. Don't worry about that. So what we're going to say is that epsilon is going to be close to 0 for large enough scales, right? And this is because that tapering is never going to get down to some ridiculous limit. You've still got to put stuff in through it, and it's also just not going to be that fast, right? So kind of went to this effort to make these to sort of incorporate, allow for the possibility of scaling in the tube shapes, but in the end, it's, we can sort of make the argument that we might as well just have a, This may all be about tide. I don't know. You can straws will be fine. All right. Milked it pretty strongly. Okay, so So here, let's talk about blood networks, and maybe I can get through this now. Okay, blood networks. So we're going to say, right, the velocity of the capillaries, it's not going to go out of control. Certainly at the capillary, it's sort of it's nice and slow. The aorta, it can't get too fast. Things are going to explode. Material is going to be costly, so you certainly don't want to have a ridiculous network, right? So you're going to make it fairly much like this Gassner and Newman thing for the Boston commuter line, and so on. You want it to basically go out to the capillaries as reasonably fast as possible, right? It's not going to do some loops and then run out. Some weird things up here with the circle of Willis. The term for these shapes, by the way, is star convex, which is a thing. It just means that there's one point where the heart is that you can directly see everything in the shape. They're not actually just convex. So, cardiac blood networks, they fill a d-dimensional volume, and we're running around in 3 dimensions. This is well known, right? I mean, just by looking at organisms and also someone actually trying to compute it. This is a paper by Stahl. The volume of network scales as volume, just does. Right. So sink density has to therefore decrease, right? Because we've got these two things. The volume of network has to scale as a volume, but we've got this for our best network. So this is an argument from the network. This is an argument from reality. So the density of sinks has to go down for this to be true, right? This is actually scaling a bit faster. So this is v to the 4/3. So we'll need I said the wrong. Yeah. So we'll need a minus 1/3, right? So from this very simple model, the density of sinks has to go down for this optimal network. Yeah, that's a good thing. So that's a result. And then the rate of overall energy usage, right? So it's going to be the density of sinks times the volume, which volume we say is proportional to mass. And so all of that comes out to be d minus 1 over d. And so for 3-dimensional things, we have 2/3. This is a purely geometric argument. Oh boy. So, it's possible you could get a higher exponent, less efficient thing, I don't know. But here's the thing that's never really said much, is that 3/4 is not great, it's higher. It means that these organisms are not This is not when they're performing at their maximal output. This is when this is supposed to be their basal energy metabolism. So you want that to be, you want it to be efficient, right? So this is what we would expect from that kind of simple, scaling of surface area story. But now this is a network thing. Now it's a network thing. And in fact, this is quite a nice result, right? So as we had, the number of sinks scales as volume to the 1 minus gamma max, right? So for isometric, that's volume to the 1 minus a third in 3 dimensions. But for, say, our pancake ones, it's going to be volume 1 minus a half. It's volume to the half. So the metabolism will actually scale as volume to the half. You're not going to have, right, these pancake cows, their metabolism is actually going to be lower. Right? They're going to be lower, but they're going to have this higher surface area. So they're going to be like, it doesn't match. Their surface area will be scaling as volume to the 1, and their metabolism, if you like, or their sink is going to be scaling as volume to a half. Not good. And the only place that you get this thing matching with surface area is 2/3. So this, I think, is a profound thing, right? And so here it is, right? Surface area is 1 minus, it's volume to the 1 minus gamma min, and the number of sinks is volume to the 1 minus gamma max. So they're only the same when gamma min is gamma max, and that means all of these exponents are the same, and that only happens when it's isometric. So this is, look, the idea of this, it's evident that right, we have a network that's supplying nutrients in all these organisms. Thinking about the constraints on that is incredibly reasonable. It's a good thing to do. And if you strip all of this other stuff away, you do, I think, get this rather quite beautiful result, that the most efficient network, in this very simplistic thing, this most efficient network will match with the surface area scaling. These are 2 very different stories. They only match when we have isometry. Yeah, the pancake ones would lose heat too fast, right? And so they wouldn't be able to keep themselves warm. You'd have to make special, Etsy would have to make special cardigans for their pancake dogs. We definitely have pancake dogs. Not cats, you couldn't do it with cats. They would defeat it through treats. Okay, so I don't know, I think this is quite a beautiful thing. And there it is, yeah, right, it's right there. 1 minus gamma min, 1 minus gamma max. Okay, tarot card, yeah. So as we've seen, the exponent, it works pretty well up to maybe 10 to 30 for mammals. It's great for birds. It's madness, the whole thing is madness. Maybe there's a different kind of scaling, and there's another paper, it just came out, I didn't put it in, but so instead of, say, this quadratic fit, which is a pretty crazy thing to do, like that's just not founded in anything. I mean, it's mathematically you just do it, but a quadratic fit in log space, I don't even know what, yeah. Because I think you end up with mass to an exponent and then mass to another exponent times log of mass. That's you'd have that correction in there. Okay, is that right? Yeah. And we have this story, right? This is breaking scaling from this economist paper. This is from a long time ago. And I know I've repeated this slide. I should repeat it. I did say recall. Good. Yeah. Self-awareness. Maybe it's good. Yeah. So like I was trying to say, they're just now. So this one, and then another.
This is an interesting thing. Let's go to the surface, and temperature. We've got energy expansion. This is Stefan Boltzmann, famous thing from physics. So this is the amount of energy given off by a shape, by some object exchange with its surroundings based on radiation.
And this is the prefactor is very much roughly 10 to the 5 to the regression, right? And this is in ergs per second. And this is like sigma is a I can't remember what's in sigma, but it's the Stefan Boltzmann constant. We're going to put that number in. We're going to put in some rough ideas of scaling and so on, and we can get this estimate out. And in fact, the regression gives you this. So it's pretty good. It's not bad. It's not bad. Heat's given off in a number of ways, but certainly radiation is a big part of it. Again, that's why they can find you at night. So even that works pretty well. Okay, so I think I'll talk a little bit more about it on Tuesday, and then we'll move on to some other things. I guess I want to recap briefly the facility location thing. I just want to, I know you've seen it, but I just want to go through it again quickly, and I'll point to the stuff we did in parks, but just because it's sort of part of this package, I just want to sort of highlight what's in there again. You know, where do you put your Starbucks and your hospitals and those things? Just such a great story. And I'd hope to have the next piece for you, right? But we're getting close to the connecting that with the hot model and some other, and all of machine learning. So there's that. That's really exciting. But then I think we'll move on to some other pieces, and the next thing is random networks, which is a beautiful, rich area of things, just a good thing to know about, and some really fun little mathematical pieces with generating functions and so on, and well, bipartite networks, such a profound reality. So we'll do some of that, and then we'll find our way into some other tarot card space. All right, but it's madness, and hopefully I've conveyed that in a way that you believe me. I am the unbeliever. All right, thank you. Thank you. Right.